Okay, good morning. I have one administrative note about the assignment, which is due on the 27th. When I handed out the assignment, the intention was that each student does it by himself. That's why each one got his own disk drive. But I see that many of you group together in groups and you're doing it together. So that wasn't the intention. However, it's too late because some of you are already deep into it as groups. So be aware that if you do it as a group, you have to write down. If you want to, you can even hand in one assignment and write down the names of the people in the group. Because if you do it as a group and you hand it as individual assignment, I would think you copy it from each other, because I'll see the same sentences, the same data, and then you will fail, right? So because if you copy in an exam or anything, you get 0 automatically. Okay? So you have to write down that you did it as a group and put down the names of the group. However, as a group, you'll be graded much more harshly than individual. Because as a group, you are supposed to be better than one person. So if you made, for the same mistake, if you did it as individual assignment, you'll use a few points. If you did it as a group, you lose more points. So be aware, by doing it as a group, you are looked a bit more harshly at the mistakes and what you didn't do right. Because I think that's fair, because the intention wasn't to be done as groups, but it's your choice. If you want to do it as groups, you'll just be graded a bit harsher. I mean, if everything is good, you still get perfect score as a group too. But if things are not correct, you'll be graded a bit harsher. As a 2 will be graded harsher than 1, and 4 will be graded harsher than 2, and so on. So it's your choice, because the idea was that it wasn't a group assignment, but that doesn't matter to me if you make it into a group assignment. Okay, so let's continue. Just to recapture Tuesday's lecture, because it was a bit rushed, so I just want to recapture the behavior of the two motors. We talked about the two most popular types of DC motors. We talked about the PMDC, which is also similar to the parallel wound or parallel connected DC motor. And we talked about the series connected DC motor, or what's also called the universal motor. It's called universal because it works well on AC as well. That's why it's called universal. So just to recapture, we said that the model is, if you take a battery and drive the motor, the model is there is resistance R, and there is a reverse battery which is created by the back EMF. And that reverse battery is a voltage of capital K times omega. So and this is V. So the equation for a simple parallel motor, which I wrote last time, is simply I is V minus K omega divided by R. And I also mentioned that the K, or I, is also related to torque by K, and it's the same K. I said torque is capital K times I. So since we like to plot these graphs not as voltage or current versus omega, but we like to plot them as torque versus omega, or omega versus torque. You can plot these graphs two ways, either omega on the x-axis or omega on the y-axis. So it doesn't matter, both are valid. So because we like to plot these graphs as RPM or omega versus, sorry, the other way, since I started this way last time. No, I started last time plotting omega here, and this will be torque. Okay, I can convert. In this equation, I can convert I into T divided by K. So basically, from this equation, I can replace I by T divided by K. And so I have my equation. So basically, if you rearrange this equation, okay, you have your equation. Okay? Say you cross multiply, so T times R is K times V minus k square omega. So you bring omega to this side, okay? Omega equals kv minus tr divided by k squared, or another form is v over k minus tr over k squared. So we see that it starts here with no load at v over k, which makes sense because that's the definition of k, and it will drop with the load. And the only reason it drops with the load because if there is more, because the load creates a current, because the load slows it down. As it slows down, this voltage becomes smaller, so the resistor sees more voltage across it, current goes up, and so the net voltage available is less, so the RPM is less. Or you can look at it at the reverse. If there is more torque, there has to be more current. If there is more current, there is more voltage drop, so the rotor has to go slower to match the residual voltage, because the three voltages have to add up to sum together to 0. Okay? So whichever way you want to look at it, when you look, either you look at it mathematically, okay, if torque goes up, the line has a negative slope, or you want to look at it intuitively, if you load the motor, this drop becomes bigger, so the k omega becomes smaller, it means omega becomes smaller. So this is like a perfect motor, and this is a motor, and if you drive it at a different voltage, it will just be a different family of curves which are all parallel, more or less. Okay, I'm ignoring friction and so on. Okay, so this is omega as a function of the load, and I gave you an intuitive explanation what happens if you connect the motor in series. Because if you connect the motor in series, the problem is that these k's are not constant. And the reason they're not constant, because if you recall, k was the L times B times R times 2, but if B is a function of I, and the I is changing, the k is changing. Okay? So what I did Tuesday, I said let's make a very simplistic approach. We'll say that the new k, if it's a function of I, we'll say that k itself is some small k times I. Okay? So big K was when it's constant, and when it's a function of the current, because the magnetic field is changing, we call it a small k times I. Now, we also know that torque is proportional to current in any motor, because at the end it's an electromagnet. The torque is created by the force between two magnets. If you double the current, you double the torque, because you double B. So we know that we can also say that large K is proportional to small k times torque. Okay? So certainly it's, if one is equal, the other is proportional, because there is a ratio between current and torque. But now, if the large K is proportional to torque, I can plug it in here and I can derive the equation for the series wound motor. So what I'm doing, I'm taking the same equation. So this one was for PMDC, or parallel wound motor. Okay? Now I take the case of a series wound motor. Again, to reminder, this is the armature with its coil, and now I put the field in series like this. Okay? So when I increase the torque, the B increases as well, because this creates B. So now if I plug this in, okay, so I'm getting omega equals V over KT, and this is a small k, okay, minus TR divided by K squared will be small k squared T squared. Okay? So now T cancels out, Okay? And now I can see already that I can take 1 over torque in front of the equation. So I'm getting, this part I didn't finish Tuesday. So we got up to here on Tuesday. So this is new. Okay? So if I take 1 over t out of the equation, I get v over small k minus r over small k squared. Okay, I know I can take k out as well, but I don't need k out of the equation because all that I want to prove that I get a constant power curve. Now, if I get omega is proportional to 1 over t times something, which is a constant. For a given voltage, that's a constant. Okay? So what it means that omega times t is a constant. Okay? I basically multiply both sides by t. If I multiply both sides by t, I get omega t equals some constant. Okay? And the constant here is v over k minus r over k squared. But I'm not interested in what the constant is. I'm more interested in the fact that for a given voltage, omega times t is a constant. Because if omega times t is a constant, if this is omega and this is t, I'll get a graph of constant power. Because as I said Tuesday, omega times t is power. So I get a constant power graph, and I mentioned many times that's basically as if the motor had an ideal automatic transmission. It always uses a full power no matter what the torque is. Okay? So if I have a different voltage, if I change the constant by giving the motor a different voltage, it will look like this. It will look like a family of graphs. In this case here, this is V1 and this is say V2, and V1 is bigger than V2. Okay? Here I'll get a family of graphs. This is this will be say V1, this will be V2, this will be V1 bigger than V2. Okay. So up to this line we went over already. This is only new line I added. Now I know it sounds like a circular argument a bit, that I replace the k by another k with torque. This whole thing is an approximation, but it gives you an intuitive feel. It gives you an intuitive feel how the motor behaves, and that's what you get. Now the reason I'm saying all this as approximations is because there is many nonlinear factors in a motor. If there weren't this kind of motor, the speed will actually go to infinity when it's not loaded. But in reality, the speed doesn't go to infinity. It ends up with some high omega, but not infinity. Because there is first of all air losses or some other viscous losses like bearings, and the losses go up faster than linear with speed. Okay, but even if they went up linear with speed, it will already limit the speed, but the losses go up second order or faster. So because of that, as the motor starts running fast, the losses go up and stop. It reach some limit, generates a minimum torque which stops omega. Now besides losses, there are some hidden losses in a motor, because there are hysteresis losses in the armature. I mentioned before hysteresis losses. The armature, as it rotates, the polarity switches. So the first part, which was N, is now S. So each part of the armature has to travel through the hysteresis loop each rotation. Because as it reverses magnetism, the hysteresis loop represents losses. So there's many things which these equations don't tell you. That there is, on top of the obvious windage losses and friction losses, there is also hysteresis losses. So there's always something like a nonlinear torque applied to the motor, which modifies this curve. So the curves actually don't look exactly like this. They may look like this for a big motor, where the little friction is gone. Or another way of saying, for a very big motor, the resistance compared to the rest of the power is very low. So the motor behaves more like ideal. Okay, so I just pass this along so everybody can look close up. It's a DC motor. This is a characteristic. And there is one more thing to talk about DC motors, and this is a type which is very popular now. It's called brushless DC. Because we talked a lot about the problem with brushes, so obviously if you can make a DC motor with all these great characteristics, but without brushes, it would be great. So this wasn't possible when the DC motor was developed, because this needs electronics. But today we have electronic switches. So the obvious thought is, why not replace the commutator with some kind of electronic switch which can switch the coils without sparking? Okay? And that's a brushless DC. Now, physically, the way it's built, because the rotor would still need a commutator to transmit power to it. So the way it's built in reverse. The rotor is made a permanent magnet. So to make a brushless DC motor, you take a permanent magnet and you make this the rotor, so it can spin around. And then you place coils, could be any number of coils in this case, around the magnet. And each coil is connected with a switch which senses the position of the magnet. So the idea is when the magnet is here, you turn on this coil, but as soon as the magnet reached here, you turn this off and turn this on. So the magnet is always chasing a coil which is turned on ahead of it. Okay? So there is many ways of doing it, but the most popular way of doing it is to use a Hall effect switch. I think I mentioned Hall effect before. Okay, when we talk about sensors, a Hall effect measures the magnetic field. So since this is a very strong magnet, it's very easy to put in a Hall effect switch. So what you do, so each coil the coils are connected, say, to one side to V. So one side of the coil is connected to plus V. The other side of the coil is connected to ground with some switch. And this is connected to a Hall effect switch. Okay? So again, at the end here, you connect the coil with some switch to ground, but it's switched with a Hall effect switch. Today it actually would be done with some MOSFET, wouldn't be done with a bipolar transistor. In modern designs, people prefer MOSFETs, but just for simplicity, I'm drawing a transistor. So the way it works, when the magnet is here, the polarity of the switches are when the magnet is here, it turns this one on. Because right now you want to turn off this coil already because it reached this coil, but you turn on this coil. So as the magnet rotates, when it reaches here, it turns off this coil and then it turns on this coil. So there is always one coil ahead of the magnet is turned on, actually a pair. Because when you turn this coil on, you also turn on this coil. So this is attracted to here and this is attracted to here. And as the magnet rotates, it always switches ahead of it. Okay? So this is what's called a brushless motor. And because the switching has no spark, it is a very quiet, smooth running motor, no EMI, no wear. There's nothing to wear here because it's all solid state. So it's a very, very nice type of motor. So it costs more because it has this electronics built in. It costs about double. For a small motor, a brushless motor is about double than a PMDC, and that's why you never see it. You only see it in high quality equipment, but you never see it in appliances, you never see it in power tools, because these things are very price sensitive. And there is another reason which makes a brushless expensive, and by now you should all know what it is.
Sealing.
Ah, very good. Remember, whenever you see a big magnet, you should say, oh no, has to be sealed. Okay? So it's very, very important. The brushless fundamentally has to be a sealed motor, and because it's a sealed motor, it has to be, let's say, larger for the same horsepower than an open motor, and that's why. Come on, I've said it 100 times already in this course. So why is a sealed motor, why does it have to be bigger than an unsealed motor?
cool it?
Can't cool it, because an unsealed motor, you can run air through it and cool it a lot. A sealed motor, you have to have outside fins. It takes a little bit more space. The best example is a vacuum cleaner at home. In a vacuum cleaner at home, the motor is actually placed in the airflow of the vacuum cleaner. Okay, so all the air you suck into a vacuum cleaner goes through the motor first. Well, first through the bag, of course, because to pick up the dust. But in a vacuum cleaner, you have a bag which picks up the dust, and all the air which comes through the bag goes through the motor. So it has a huge cooling, because it's a huge flow, right? So because of this, a 1 horsepower vacuum cleaner, the motor is this tiny, size of an orange. Okay? But they also don't last very long, because some dust manages to get through the ceiling, and there's more wear on these motors. That's why a vacuum cleaner motor doesn't last long, but on the other hand, it only works an hour a day, so it's the most. But if you ran continuously in a vacuum cleaner, it wouldn't last very long. But the main thing is you can get any horsepower you want out of a motor if you can cool it. Because the regular DC motor, there is nothing to demagnetize. Right? The only limit to the power is saturation, magnetic saturation. But if you cool it aggressively, you can get huge powers out of a little motor. Okay, so with this we end the section on DC motors. There is a lot more to talk about DC motors, but again, the course is very short, so as long as you know the essentials. Okay. By the way, what do you do about the sparks? We all know that a DC motor has to have sparks. So is there something we can do to help a little bit with the sparks?
Put it in oil.
Pardon?
You can put the motor in oil, or encase it in oil.
That is not effective, because then you're back to sealing. It has to be sealed, and the viscosity of oil is so much more than air that the motor will waste most of its power just spinning the oil. Matter of fact, it will get hotter, right? Because it will spin the oil. The friction in the oil will be so high that the oil will get hot. So if you ever took apart some DC motors, maybe you have noticed it, there is some little trick you do which helps with the sparks. And whenever you see contacts with sparks, not just in a motor, you always do the same trick. So just try to remember, if you opened any time something which has sparks, there's always a little trick you do. Nobody thinks of it? Okay. Did anybody work on their car, on an older car, before they had electronic ignition, motorcycle, car? In a car there is some contacts used to break the ignition coil to make pulses. Must have been seen that on an old car, okay? So what's the trick they do there on the ignition points in the car? You must have taken apart relays which connect some load, and there is the same trick there. Every place there is a little spark formed, same trick is used. Capacitor. Okay, so basically whenever you have a contact, let's say you have an electrical contact which has to connect an inductive load. Okay? So when you open the inductive node, there is a spark. The reason there has to be a spark, because remember, this has 1/2 Li squared of energy stored in it. When you connect it, where does this energy go? It has to come out somewhere, so it comes out as a spark. And the reason it has to spark is the voltage here, in theory, goes up to infinity. Because if you open the contact and you break the current, let's say no matter how fast you open the contact, all this energy has to come out somewhere, so it breaks down the air gap. It doesn't help if you open it faster. If you open it faster, the di to dt is only bigger. Okay? I don't know if you remember this from electrical engineering, but the induced voltage is L di to dt in a coil. Okay? So basically, if you break the current faster, you only get a bigger voltage. So it doesn't matter how you do it, it's actually better to break it slower, but you can't. With contacts, either it's on or off. So you can't, it's not like a resistor, you can break it slower. So theoretically, a spark has to happen because L goes from I to 0 instantly. So you have an infinite di to dt, so theoretically there's an infinite voltage. Okay, but a capacitor is one of those devices which doesn't allow the voltage to go up fast. Because if you have a capacitor, you have an opposite effect. You have the current is C dV to dt. So a capacitor is something which will require an infinite current if the voltage changes instantly. Okay? So basically this will have to generate an infinite voltage when you open it, but a capacitor will never allow an infinite voltage to be created because you'll need an infinite current. Okay? I mean, I'm assuming that's not the first time you see that, right? So you know that. Okay, so if you put a capacitor here, okay, it will not allow the voltage to develop quickly. And because of that, it prevents a spark. But you have to put the right value capacitor, because if you put too big a capacitor, you get some other problems. You basically get oscillations, you get ringing. So you have to put and it turns out that for almost everything on Earth, the value is 0.1 microfarad. Okay? And that, okay? And sometimes you put a little resistor. Can somebody guess why you add a resistor? Again, that's an electrical engineering question, but it's something which is also common sense. If you put a capacitor like this, why do you have to add a resistor? Or at least, if it's bigger machinery, you have to add a resistor. Yes?
Can you tell me to dissipate the load that goes to the capacitor?
Very, very close. Okay, the answer is very simple. When you open the contact, the capacitor will charge up. Okay? But when you close the contact again, you have the opposite problem. When you close the contact again, you're taking a capacitor, causing dV to dt to be infinite, so the current will be infinite when you close. So when you close the contact again, you have the opposite problem. It wouldn't spark when you opened, but when you close it will weld together. So this resistor limits the current on closing the contact. Is that clear? So almost everything on Earth works with 0.1 microfarad and 100 ohm. Don't ask me why, but whenever people experimented, it's more or less ends the same. Like all of the telephone equipment in the world works with this combination. When you have motors and you are worried about RFI, in motors usually you don't even bother with a resistor because the voltages are small. So if you have a DC motor, you have a coil, an armature, and there is sparks here. Okay? Typically you put a little capacitor, 0.1 microfarad. This is very important if you do experiments which have low-level signals in the lab, and you have some DC motor which has to mix something or turn something, and the noise from the DC motor gets into your op-amps. So the first thing you do is, of course, shield everything, but if shielding doesn't help, you put a little capacitor on the motor. So when you take apart any motor which goes in an airplane, it already has this capacitor built in. Because motors go in airplanes are all shielded. This is a motor, this shaft. Inside the motor there's a double case, and there's already a capacitor built in, and sometimes there's even two little inductors in series. And this is the wires come out. So this is already built into the motor. Why the little inductors? It's a low-pass filter, right? If you have a capacitor and inductors, it's a low-pass filter. So not only does the capacitor suppress the arc, but you build a low-pass filter because the current looks like this. There's these spikes for commutation, so you put in a low-pass filter to smooth it out. Okay? Good. Okay, so there is other things than a capacitor which you can put, which are a bit more sophisticated. You can put some nonlinear resistor. You find that sometimes too, like a varistor, what's called a varistor. Anyway, it's too much detail. Okay, so now there is a, okay, so you are passing along the motor, right? Look at it, good. Now there is some piece of history when Nikola Tesla, I'm sure you all heard of Tesla, but when Nikola Tesla was a student like you, the professor showed them a DC motor, just like I showed you, and showed them the sparks, just like you can only see on the video. Okay? And Tesla, who was your age, raised his hand and said, why can't anybody design a DC motor which doesn't make sparks? Because the professor explained the same way as I explained what's bad about the sparks. So in those days there was a tradition that the professors were very arrogant and always insulted the students, and that was considered good teaching. So the professor said, well, Mr. Tesla, nobody succeeded in doing it, but I'm sure you are so smart that you can invent it with no trouble at all. Okay? So the whole class laughed at Tesla, and Tesla was a very sensitive soul, so went home depressed. And a lot of time, public humiliation is a very strong motivator for people to go and do great things. I'm serious. There's many inventions which can be traced to publicly humiliating the inventor over it, like the invention, Haber's invention, and so on. So Tesla went home and was obsessed with inventing a motor which doesn't make sparks. Because he was so humiliated, and within a year or two he invented it. Okay, and this is what's called the whole family of motors which are based on rotating fields. Remember that I said that originally when we started with motors, I said there are basically two types of motors. Motors which commutate and motors which have a rotating field. So this kind of in a nutshell summarizes all the motors in the world. So until now we talked about motors which commutate, but now we're going to talk about the other side, motors with rotating field. So, is there anybody here who doesn't know what a rotating magnetic field is and how you generate it? Because I want to know what detail to explain it. You don't know. Is there anybody else who doesn't know how you generate a rotating magnetic field? Okay. Anyway, I still should explain it because I suspect that not all of you really understand it in depth. Okay, so when you take two coils, let's say you put a coil here and you put a coil here, okay, so this is a magnet. This becomes a magnet north-south, and this becomes a magnet like this. When you connect the two coils to AC, let's say you connect this to AC, okay, and if you connect it to the same sine wave, let's say you connect it to sine omega t and you connect it to sine omega t, okay, if you do it like this, what will be the resultant magnetic field here? So one generates a sinusoidal magnetic field in this direction, one generates a sinusoidal magnetic field in this direction. What will be the resultant magnetic field here? 45 degrees, obviously. It will be the same thing. Okay. What happens if I switch one of the coil instead of sine, I give it cosine omega t? What will be the magnetic field here? Okay, so. Okay.
Rotating?
And why would it rotate?
Is it out of phase? Or is it?
So why does it cause it to rotate? You are correct, you're 100% correct, but why? Yes?
Mutual induction to
Nothing to do with it. By the way, when coils are at 90 degrees, there is mutual induction is 0. Okay? But, yes?
Each of the coils is energized at a different time, so as the coil rotates, it kind of...
But why would it rotate? Why wouldn't it jump back and forth, back and forth? Very, very close. Okay, so anyway, so I see an explanation is actually in place about rotating fields. Okay, so think about how sine and cosine were defined when you were taught in school about sine and cosine in high school. The way sine and cosine were taught, there was a rotating vector, that's a unity vector, and you were told, if this is theta, you were told that this projection here, or actually you were told that this is theta, That doesn't matter which is theta. If this is theta, you are told that this is cosine theta, okay, and this is sine theta, okay? And the way you were explained how sine and cosine changes polarity, that this vector was rotated around. In this quadrant, sine and cosine are positive, okay? And then as this vector rotates here, the cosine becomes negative, the sine stays positive, and so on. Do you remember this explanation? Okay. Now, this is also true in reverse. If you take two vectors, which one is sine, one is cosine, and you add them together, you'll get this vector. So if you take these two vectors and each one of the vectors will follow the full sine wave, the sum will be a rotating vector. Because that's exactly how you were taught what sine and cosine are. Okay, just reverse the process you were taught in high school what sine and cosine is. Okay? Good. So now if we take two vectors, this is really actually two vectors. One vector here is sine omega t. This is this vector, and this vector is cosine omega t, because they are fed from sine and cosine. The resultant will be a vector which rotates. Okay? So now what happens if you put a magnet inside here? So let's erase the rotating field. Okay? So let's say now near these two coils we have a shaft, and we put the same magnet as in a brushless motor. What will happen to this magnet? Rotate, because it follows the field. If the field is a rotating vector, just like this vector, the magnet just follows the field. Same as in a brushless motor. Okay? So is it 100% clear why this magnet will start rotating? Okay. So this was Tesla's invention. So after Tesla went home humiliated, he thought about it a long time, and of course it helped. He was very smart, because there were other students humiliated who didn't come up with anything. but being smart, he thought about it, and he is the first person who conceived the idea of a rotating field, and that was a new idea. Today the whole world is based on rotating fields, right? But it's the first time somebody thought of the concept of making a magnetic field rotate electrically. Okay? Now once you have a rotating field, it opens up a lot of possibilities. But the first thing is that you can put a magnet in a rotating field and you get a motor. Now the rotating field can be made by two coils or by more. You can also make a rotating field by three coils. So say you can take three coils like this. Okay, so each one has a vector. Okay, but now what phases should you feed them? If you had two coils, we fed them sine and cosine. Okay, if you have three coils, what do we have to feed them? If this is fed by sine omega t, what do we have to feed this coil and this coil? Okay, so in order to know, you have to think of this. The sum of the vectors has to be constant amplitude, because you don't want a field which rotates and gets bigger and smaller. Like the sum of these two vectors, because of the unity circle, the sum of these two vectors is a constant amplitude rotating vector, which is nice. Now if you take sine omega t and you feed sine omega plus 180 degrees, you don't get a rotating field, because you get two vectors which are opposite and they beat. You get an oscillating field. Okay? So obviously the first thought is it has to be an angle different than 0 or 180, because 0 and 180 is collinear vectors. Okay? So you look at it and say, I want a vector which is constant. So first it has to be three vectors which always sum up to a constant length. So what would you feed it with? Okay, so the easiest way is to say, look, if for symmetry reasons, if these are 120 degrees apart, mechanically, the coils are 120 degrees apart. Okay, let's do the sine waves also 120 degrees apart and see if I get a rotating field. So let's say we feed this with sine omega t, we feed this with sine omega t plus 120 degrees, and we feed this with sine omega t plus 240 degrees. So what we are doing is we are feeding it with three vectors. The vectors have to be positioned the way the coils are, because the vectors simply follow the axis of the coil. So if the coils are 120 degrees, the vectors have to be 120 degrees. Okay? Now if you add together, if you take sine omega t plus this, you are going to get a constant length vector. Okay? Because if you add these two vectors, you can see you'll end up with a rotating field, three constant length vectors. Okay, there is something unique about this arrangement compared to this arrangement. The unique thing about this arrangement is that the sum of the currents will always be zero, because if these are the three vectors, one is sine omega t, one is in space. It's 120 degrees in space because the coils are 120 degrees in space, but also in time it's 180 degrees. So not only is the vector pointing at 120 degrees, but the phase is also 120 degrees. So this is omega t plus 120 degrees. And again here, it's omega t plus 240 degrees. Okay? So if you add those three vectors together, okay, you get a unity length rotating vector, because the components are also phased in time. In other words, if you take three sine waves at the same phase, add them together, you get exactly zero, because you get three identical vectors added together. But because this is a different phase and this is a different phase, you get a rotating vector. Okay? And you can do the math to see it. Okay, so what I have here, okay, let's see.
Did Tesla's initial design have three coils or
two? Okay, Tesla's design had two coils, and then he thought for a long time and he realized three is better. Okay, now that is a very, very good question. I don't expect you to know the answer. Why are three better if two already give you a perfect rotating field? Why? Yes, why? Why? Three-phase power is better for transmission. Why? Okay. Pardon? But why? This is a perfect unity length rotating vector, so the magnetic field is identical. If you look at the magnetic field here, you look at the magnetic field here, they are identical. It's a unity length rotating vector. Yes?
You only need one additional conductor?
Pardon?
You only need one additional conductor to get three power?
You're very close, but not quite, because here, see, right here I only need three conductors, because I can take the three coils, I can take the two coils, so I have line 1, line 2, and I can have a neutral here. So I only need three conductors going to the motor. Now here it appears I need four conductors, because I can connect the coils together, and this is neutral, and then I have line 1, line 2, line 3, so it looks like here I have four conductors, here I have three conductors. Of course the currents will be different in the conductors, but where is the saving?
Aren't you like maintaining a higher duty cycle, like you're maintaining a higher level of 3 increment or something like that?
That if you rectify the three-phase, but not in AC. In AC there are still sine waves. Each one of these lines carries a sine wave. So if you put a ammeter on the lines, it carries a sine wave. Okay, why doesn't this come on? Okay. Oh, because the light is on. Okay. So yeah. So hold on just a second. I want to get this on. I see why. This one. I have to cross this one. Okay, good. So, okay, any other guesses? So why did this take over, although this generates a perfect rotating field? Yes?
Sums to 0 at the neutral?
Perfect, beautiful. Because it turns out that there is no current in the neutral because the average of these three vectors is always 0. I mean, you can do it by vectorially, you can also do it mathematically. If you take sine omega t plus sine omega t plus 120 plus sine omega t plus 240, and you do the math, which I wouldn't do because it's too lengthy, but you know how to do it. This is sine alpha plus beta. So you break it down into the product, and this is sine alpha plus beta, and then you sum it all together, you get 0. Okay? So, because you get 0, and remember, don't get confused between the phase, which is 120, and the physical position of the coils, which is 120. Because you can take the same three sine waves and also apply them to coils which are not at 120. So you can make, in theory, you can make something like this, two coils at right angles and one coil like this, and you can still apply the three phases of the sine. You'll get some kind of a distorted rotating field. So don't get confused between the temporal shift, which is 120 degrees for each phase, and the spatial position, which we made the same. There are two different things. Okay? Okay, it just happens to be that the right temporal shift has to match the spatial shift to get a unity vector rotating field. But in theory, you can take three coils in parallel. You can take three coils which are parallel mechanically and also connect them to the three sine waves. But this will only generate an oscillating field, not a rotating field. Okay? So, because the sum is 0, there is no current in the neutral. And because there is no current in the neutral, you only need 3 wires to run the 3 phases, not 4. That's why a 3-phase motor only has 3 wires coming out of it, not 4. Now here you also need 3 wires. Line 1, line 2 is neutral. Okay? So where is the the reason why you need the neutral here, because when you take sine theta plus cosine theta, the sum is not 0. So some changes actually. Right? It goes from 1 to 1.4 back to 1, 1.4, right? So this sum is not 0, you need this wire. So, okay, so we concluded that here you only actually need 3 wires, not 4. Here you also need 3 wires, so we still don't understand the gain. Both run on 3 wires. So where is the gain? But you were very close, keep thinking. Okay. Why? It's a function of the current. Okay, so the answer is this. For a given current, if this was a sine wave of 1 amp, let's say 1 amp, let's say coils are identical, currents are identical. Okay, if so this was 1 amp and this was 1 amp, okay, and this would be fluctuating between 1 and 1.4 amp. So you can calculate the RMS current, let's say 1.2 amp. Does everybody understand why that's fluctuating between 1? Okay, good. So roughly you have 3 conductors, they carry 1 amp, 1 amp, and around 1 amp, and they give you 2 magnetic fields. Okay? Okay, now let's say you take the same 3 currents here and you have the same coils, the same 3 currents. Okay? So you get 1 amp, 1 amp, 1 amp, here you get 0. Okay? But you get 3 magnetic fields. Okay? So here you get 3 amp and you get 3 times a magnetic field B. Okay? Now here you get 3.2 amps, 1 amp, 1 amp, and 1.2. Here you get 3.2 amps, but you only get 2 magnetic fields. Okay? So for the same torque, say torque is proportional to B, so this will generate 3 torque units with 3 amps in the conductors. And that matters for the power loss in the conductors. So this you have 3 conductors, each one carries an amp, you generate 3 torque units. Here you have 3 conductors, you need a little bit more than 3 amps, but you only generate 2 torque units. So this is more efficient in power transmission by 50%. Right? That's the secret. Is that clear to everybody? Yes. Pardon?
You lost the button.
Oh, I'm sorry, thank you. It's bad for the video. Okay, good. So, okay. So now what's left is to do some demos so you'll remember it better. So what I have here, I built a little demo because I always suspect that in spite of all the explanations, students still don't understand the three-phase business. So what I built here is a little demo which has 3 coils, has a compass to see the magnetic field, and has 3 compasses just to use as ammeters, which measure the 3 currents. Okay, and we'll plug this in. Okay, yeah. Now, in order to generate 3-phase, because this room has only 1 phase, the easiest way to generate 3-phase is use these things. These things are, which I mentioned before, these things are what I mentioned before, they are called VFDs, or variable frequency drives. This is a standard thing you use to drive motors at variable speed in industry. But the nice thing about it, it takes a line voltage, rectifies it, and then chops it to 3 phases. But because it rectifies, even if you feed it from 1 phase instead of 3, it still works. So these are designed to take 3 phases, rectify, make DC, and make synthetic, use 3 phases at variable frequency. But because it has a rectifier on the input, you can plug it in 1 phase, it still works. Okay? So we'll hook it up to the 3 phases. Good. And we'll turn it on. Okay, so what you can see here, and I'll show it with a pointer. Okay, so these go, the ammeters just go up and down, but you can notice are out of phase. I don't think you can see they're exactly 60 degrees out of phase, but you can see they're out of phase. When one goes up, the other one doesn't go up exactly in the same phase. So these are 3 phases at 120 degrees apart. By the way, this is the classic Ørsted experiment, right? That's how this whole electromagnetism was discovered, when a compass was put near a conductor. Okay, so it's also a nice demo of the Ørsted experiment. So here are 3 phases, each 120 degrees out of phase. When you sum them with 3 coils, you get a rotating field, because you can see the compass keeps rotating. Okay? And by the way, there's no return wire, as you can see, because I'm relying on the fact that it sums to 0, so there is no return wire, it's just the 3 phases. And that's how all 3-phase motor works, they don't have a return wire. Okay? The neutral in a 3-phase system, this point, is actually connected to ground, just like the neutral in a house in a 1-phase system. So you don't have to bring it, you can connect it to ground outside the plant. Okay, so if you go outdoors and you see these high voltage transmission lines between cities, they don't have a neutral. They only have 3 wires. Like the big towers, so you see, always have 3 wires. The neutral is created locally by connecting the ground to the neutral outside the building. Why outside the building, not inside? I spent a long time explaining that. Like in a house wiring, why is the neutral, which is same as ground, why is it not connected to ground inside the house? Why do you have a ground and a neutral in the outlet? So, when we talked about grounding, I went to spend half an hour just on this point. No. Come on. I even told you at the time that you can graduate without understanding sensors, but you shouldn't be allowed to graduate if you don't understand how your house is wired. Okay. So, something to do with safety. Okay, I'll say it one more time, but you really should remember it. If a neutral is connected to ground, you cannot protect yourself from being electrocuted, because the way ground protects you from being electrocuted, it's connected to the housing. to the housing of equipment. Say you have a fridge, the housing is grounded. So if anything inside shorts to the ground, it will blow the fuse. And you can detect it with a ground loop switch. If it's a really dangerous situation, you have this ground fault interrupter, which actually measures the leakage to ground. Okay? But if the neutral was connected to ground in the house, there will be no difference between current flowing through the ground or current flowing through the neutral. So in other words, if the neutral and ground were connected inside the house, if you're inside the fridge, instead of returning the voltage through the neutral, it will return the voltage through the housing of the fridge. There will be no difference. It's the same wire. Okay? But then the outside of the fridge would be live, say if the neutral was disconnected. Or depending where it touched it, okay? But basically you want the housing of equipment to be a separate wire than the return wire of the power for safety. Okay? For several reasons, and one reason is that you can tell if the current is going through the housing or through the real return where it should go. But if the two wires are the same, there's no way to tell. So you should remember that. And so you should remember that if you take an ohm meter in a house and you measure neutral to ground, you get 0 ohms. So it is electrically connected, but the connection has to be done outside the house, so you can inside the house sense if the current returns through neutral or ground. And that's how GFI, ground fault switches, the one which have a red button on it says test, that's how they work. Okay? So please don't forget that. It will be very embarrassing if you are a UBC graduate and don't understand how your house is wired. Okay, so back to rotating fields. Now you see how the rotating field works. Okay, if I change the frequency, nothing will change here except it will go faster. This is slowed down. This is slowed down to 1 hertz. Roughly, actually, it doesn't say here. Okay, so anyway, this is slowed down to about 1 hertz, just so you can follow it with the eye. If this was run at 60 hertz, at the full rate, you wouldn't be able to see anything, because this will just vibrate and this will spin so fast you wouldn't be able to see anything. Okay, so this is called a rotating field motor. The most popular is 3-phase, but there is enough of those in 2-phase as well. Okay. Very good question. Let's see if somebody can guess here. Exactly correct. Because these things, remember, these things generate a sine wave by PWM. So they have so many pulses per second to generate a sine wave. So when you want to generate 60 hertz, okay, you do it like this. You want to generate a sine wave of 60 hertz, so you generate a narrow pulse, a wider pulse, a wider pulse, a narrow pulse, and so on. But if you want to generate 1 hertz, there is not enough pulses here. So it's, you see the jerkiness, because if this is 1 hertz, okay, you basically don't, I should say it a different way. This thing relies on the filtering effect of the inertia and the inductance. So when you generate these pulses at a high rate, what you really get is you get something like this. You get the inductance of the motor and the inertia of the motor providing the filter. But if you want to do it at 1 hertz and you just generate a couple of pulses, okay, the filtering effect is not there. So you get some kind of a very jerky waveform, because the thing is so slowed down that you actually see the individual pulses of the PWM. Yes?
So if you want 1 hertz, isn't your switching frequency to your fundamental frequency a lot higher?
Yes, but there is no filtering. There is no filtering. This is not designed at all to work at 1 hertz, because in a normal motor drive, it only dwells at 1 hertz for a second. In a normal motor drive, you ramp it up. The motor is not designed to operate at 1 hertz. Now, the reason why the motor is why this and the motor are not designed to operate at 1 hertz, because the motor is rated for a given current. Okay, so the power it outputs is current times voltage. Okay, if you run the motor at 1 hertz, you also have to give it a voltage 60 times less. Otherwise the current will be too high, because the inductance is 60 times less. So because of that, there will be no power. So if you take this, connect it to a motor, run at 1 hertz, the motor will have no power. So because of this, they don't bother to filter and smooth it out at 1 hertz. It's true that the switching frequency, it's true that in terms of number of pulses, you should be able to filter and smooth it out even better because you have more pulses. But this doesn't do it. It's not designed to work like this. So instead of doing, if this is 1 hertz, instead of doing a lot of pulses and applying the same filtering, it just gives you like 1 or 2 pulses. It's just because it's not designed to work at 1 hertz. It's not a fundamental reason. Fundamentally, it should be a smoother sine wave at 1 hertz. Okay, so let me explain again why it's not designed to work at 1 hertz. Because what limits the current, if you run it from AC, what limits the current is not the resistance but the inductance. Because remember that in AC, the impedance, okay, is the square root of R squared plus 2 pi FL squared. Okay? That is the impedance. And the current through the coil is V over Z, not V over R. When we talked about DC motor, since it's DC, we could just use R. But when you talk about AC motors, okay, it's this. Now, we also said that in motors, to be efficient, R has to be much smaller than 2 pi FL because the R is pure losses. It represents pure losses. 2 pi FL, when you load it, it actually represents the work done. Okay, the energy stored in the magnetic field and so on. So because of that, we can say roughly that what limits the current is just the inductance. So if you lower the frequency, you have to lower the voltage to maintain the same current. Because a motor is always rated by current, not by voltage. The reason a motor is rated by current, because the heating in the motor is I squared R. This doesn't generate heat, because a pure inductor doesn't dissipate energy. Okay? Like same as a pure capacitor doesn't dissipate energy. The energy is only dissipated in the resistive part. So we said in a DC motor, typically that's like 10% of the power. And same here. Okay, so basically the thickness of the copper wire has to do with the maximum current, and that's given. It doesn't matter what voltage you put on it, you cannot exceed the current. But if the impedance, if Z goes down from 60 Hertz to 1 Hertz, if this is 60 times less, you have to make V 60 times less. Okay? Now the power is V times I. I mean, to be strictly correct, is V times I times cosine phi. Cosine phi is the phase angle between voltage and current. So if you really want to be correct, it's times cosine phi. Okay, but if you keep I constant and you have to lower V 60 times, the power is only a 60th of the full power. So the motor is pretty useless. So because of that, these things are not designed. Although they could make a beautiful 1 Hertz sine wave, the motor will have 1/60th of the power. So it's useless. So these are designed when you ramp to go through the 1 Hertz, 2 Hertz, 3 Hertz with just a few pulses, and that's it. Okay? So it's not a fundamental reason, it's just the way VFDs are designed. You don't expect a nice sine wave out of them at low frequency. Yeah.
Why do you have to lower V at lower?
Because I has to be kept constant. To go back one step, when we talked about actuators, we said it's made of copper, and we said the copper can carry roughly 10 amps per square millimeter. Okay? So let's say the motor is wired with a 1 millimeter wire. So you can only give it 10 amp. Okay? Because otherwise it will overheat. Now this 10 amp, it doesn't depend on the frequency, it doesn't depend on the voltage. Because every coil is only limited by current, not by voltage or frequency. Okay? So if the motor is a certain wire and the nameplate says 1 amp, no matter how you drive it, you cannot exceed 1 amp because the I square R, the heat, is only proportional to the current. Okay? So if the current has to be kept constant and Z is 2 pi FL, F goes down from 60 Hertz to 1 Hertz, right? Then Z will go down 60 times. So the voltage has to go down 60 times, so the motor has no power. Is that clear to everybody? Okay, so that's the reason these things are not designed to make a nice sine wave below 10 hertz. At 10 hertz it already looks like a sine wave. But it's just an economic consideration. It's nothing to do with theory. Okay? Yes?
How does the spatial distribution of the windings affect the magnetic field? I seem to remember that you wanted to have a sinusoidal.
Now you're getting into subtleties. Okay. So now, okay, so let's talk about that. That is, I wasn't going to cover that, but since you asked, let's talk about this for a minute. Because if you just have 3 coils in the air with big air gaps, and you put a magnet here, that magnet will rotate very smoothly because the magnetic field will be exactly the superposition of the 3 vectors. But when you make a motor, you're trying to minimize the air gap, because if your air gap is big, you need more current to get the same B. Remember the formula when we talked about B? It was proportional to a whole bunch of things, but at the end it was divided by X. X is the air gap. Right? That was when you did the formulas for an actuator. Right? This was here. There was A times mu times n squared, but it was all divided by the air gap. So when you make a motor, you're trying to make a very small air gap, just like the DC motor I'm passing around, and you try to make it like this. You put 3 coils. This is a magnetic circuit. So the actual lamination of a motor looks like this, and you put the coils here. And the magnet is also shaped rounded to minimize the air gap. Now when you do that, there is a problem, because the magnetic field changes abruptly from here to here. It's not a smooth changing magnetic field in free space. The magnetic field lines, they are very dense here, and here they go nearly to 0. So what you will have cogging. Like as this rotor rotates, here it's under a very strong magnetic field. Now it comes out of here, and then when it lets go, there is a jump in the magnetic field. So instead of a nice smooth rotation, you will have something a bit like this. It will be jerky. So what you're trying to do, you're trying to lay out the windings and the poles to get a smooth transition of a magnetic field, that it will be spatially here also gradual or sinusoidal. Okay, and then it will rotate. But you don't want the transitions to going from air to metal, metal to air, which give you vibrations. So there's 2 solutions for that. One solution for that is to lay out many windings, so you can still have 3 phases, but you can distribute them over many slots. And the real motor, when you look at the real big motors, they don't have 3 coils and 3 slots. They look like this. They have many slots, maybe 20 or 21 or whatever, and the coils go like this: 1 coil, 2 coils, 3 coils. So they still have the coils connected in groups to make 3 phases, but the coils are distributed into many slots. Okay, so this is to better utilize steel and to avoid big air gaps, which cause jumps. But there is another trick you can do, and the other trick you can do, which is typical of all motors which you take apart, when you look at the motor from the top. So when we drew the motors, we always said, say this is a rotor, and we always imagined it to be like this, to have these are the poles, and say this. If this is a magnet, or if it was a DC motor, we imagined it to be the coils like this. Okay? But if you take motors apart, you realize they don't do it like this. What they do, they take the rotor and they skew these. So if this was the magnets, or if this was the coils, instead of making parallel, they skew them a bit. Okay? So basically the whole rotor looks a bit twisted. And why is that? That's nothing to do with engineering, just common sense. Why does slight skewing of the magnetic material, either here or in the stator, why does slight skewing make the motor smoother?
Because where it's acting on the shaft is at different.
Exactly, because you don't have the whole magnet disengage from the pole at once. If it's skewed, if you have a moving magnet in the rotor and you have a stator, and the moving magnet approaches the rotor, so suddenly the magnetic field increases at once when the air gap becomes small. But if you have it a bit skewed, the top engages just when the next one disengages, and then the engagement is gradual, and when it comes to disengage, it's already engaging the next one. So there is always one part engaging in the magnetic field, and the magnetic field is continuous. Okay? So this is called skewing of the rotor. Okay, so the two standard tricks used, which make a real motor look a bit different than the motors I drew, is the first thing, you have many slots and many coils to spread out the magnetic field to make it uniform, and indeed you want a sinusoidal distribution. Okay? And the second thing is you skew typically the rotor, not the stator, but sometimes you see the stator skewed. So if you take apart your power drill at home, which is a DC motor, you will see a commutator with bars, but you'll see the slots in the rotor and the coils do this. So almost any electric motor you take apart will have a slightly skewed rotor. And remember, the skew has to be less than one pitch, because you don't want to short the magnets. Like if it was skewed too much, it will just short across the magnets. You don't want that, it'll create no torque. Right? So if my fingers are the poles of the magnet, and this is the rotor. So this way the rotor is attracted from one to the other. If the rotor is a bit skewed, it's even nicer. It's smoothly attracted. But if the rotor is skewed too much, it just shorts out the poles. There is no difference in force between here and here. Right? There is only a difference in force if there is a change in magnetic field. So you cannot skew the rotor more than one gap. Is that clear? Good. Okay. Any questions about rotating field motors? Good. So, do you have any rotating field motors at home? Yes. Give me an example. Pardon? Excellent example. Hard drive, if you take it apart, even the hard drive you all have, if you look at the hub, you see 3 wires coming out of it, sometimes 4 with a neutral. Okay, that's exactly a classic 3-phase AC motor. But you actually have a lot more than that. Where else do you have rotating field motors at home? Each one of you has a dozen rotating field motors.
Washing machine?
Correct. Because when you make motors bigger, there is a tendency to use a type of motor called induction motor, which we are going to talk about next week. And this is a rotating field motor, but a bit different construction. It doesn't have a permanent magnet. Remember, this type of motor I showed relies on the rotor being a permanent magnet. And there is some issues with that, and there is a different type of motor which is still rotating field. So, okay, where else do you have a rotating field motor at home? So, washing machine, by the way, table saw. If you have a table saw, the bigger motors are also rotating field. So, if you have air conditioner, washing machine, these are all rotating field motors. Where else? The CD, DVD drive, of course, like a hard drive, that's also a rotating field motor. So you have to think about it this way. What is the biggest advantage of a rotating field motor compared to a DC motor? Besides no commutator, that's the biggest. What's the second biggest advantage? Very good speed control, because the speed exactly follows the frequency you give it. So every application where you have perfect speed, you have to use a rotating field motor. Because a DC motor, a brush or brushless or parallel or series, doesn't have a constant speed. The speed is a function of the load. And the rotating field motor has to have exactly the same speed as the drive sine wave, because it follows it. So say electric, like this clock here, all electric clocks, which tells me the lecture is over. So all electric clocks have to be rotating field motors because they have to be synchronized, exactly show the same time in all the rooms. Okay? So any timing motor, you have some timers at home, any timing motor, electric clock, not electronic, not the battery quartz, but the big electric clocks, all these power line operated timers, they're all rotating field motors. And for the same reason, if you have in the old days a turntable or today a DVD, CD, all these motors are rotating field motors or hard drive because you have to exactly control the speed. Okay? So we'll continue next week.